Recall that the real number alpha is called badly approximable if the absolute value of alpha minus p over q is greater than c over q squared for some c greater than 0 and all rationals p over q. Now we are going to talk about the method that will study the set of all badly approximable numbers in terms of the Hausdorff dimension. Hey guys, today we are going to introduce a method that is introduced by Wolfgang Schimidt in 1960s called the Schimidt Scheme, which allows us to study the set of the badly approximable numbers. Now let's first look at an example. We take two parameters, alpha between 0 and 1/2 and beta between 0 and 1, and consider the following game of two players, and Schimidt calls them black and white. It goes as follows. So first, black will pick a closed interval, call it B1 on the real line, and second, white will pick a closed interval W1 that is contained in B1, and the W1's length is equal to the alpha times the length of B1. And now in the third step, black will pick a closed interval B2 such that length of B2 is equal to the beta times the length of W1. And you can guess in the fourth step, white will pick a closed interval W2 containing B2 such that the length of W2 is equal to alpha times the length of B2. And we can draw a picture here. So in the first type, black will pick a closed interval so B1. This is B1, and then white will pick a closed interval W1 whose length is alpha times the length of this, which is less than 1/2. So we'll make it smaller right here. This is W1. And in the third step, black will pick a B2 that is contained in W1. And length is the beta times that of the length of W1. But this beta can be close to 1, so it doesn't have to be very small. But in the fourth step, W2 will pick a closed interval such that the length of this is alpha times this, again to be fairly small. So this is W2. And I hope this is clear. And this game does not stop at the step 4. It will go on. So finally, you consider the intersection of all those w sub i's. And you know this is just one point, because so the length of wi's shrinks by at least 1/2 each time. The length shrinks at least geometrically. And for this game, we need to determine a winner. So we will call white the winner if this intersection, which is just one point, a number, is a badly approximable number. And otherwise, we'll call black the winner. And that is the outcome of the game. The example we talk about in here is a special case of the following Schimidt game in more general settings. Now we'll talk about the abstract Schimidt games. And it has a name called FG games. Now we let M omega be two sets, and omega prime be a subset of omega. Here you can think of M as the real line, as in the above special example. You can think of omega as the collection of all choices. And you can think of omega prime as the initial choices. And let alpha be a map from omega to the subsets of M. So I use this P to denote the power set, the set of all subsets of M. And we call H function, this script H function, any function H from omega to the power set of omega, which assigns each element in omega to some subset of omega. And you can think of H as a function assigning each choice a bunch of choices. So when you choose something, this H will assign one choice to more choices. It's something like this. And you also assume this H to be H of B to be non-empty. And H is any function, any such function satisfying for C in H of B, alpha of C is always contained in alpha of B. And now let F and G be two H functions, and let S be contained in M, and consider the following game of two players. Call them black and white, as before. Remember, omega prime is defined here, and we said it corresponds to initial choices, and we choose B1 in this set omega prime. And white will choose W1 in f script f of b1 correspondingly. In the second round, black will first choose b2 in script g of w1. And in the second round, white will choose after black that w2 in script f of b2, and so forth. Because we have this containment property, we have the following descending sequence of alpha of some sets. So we will have alpha of b1 contains alpha of w1, and so forth. And we call white the winner of play if intersections of all alpha of wi's, which will be same as the intersection of all alpha of b sub i's, is contained in S, or otherwise a black will be the winner. And we will call this game the FGs game. And if white can always win this FGs game, then we call S a FG winning set. And here's another way of defining the FG winning set. Now let capital F sub n, where n is from 1, 2, 3, be the set of functions little f which has n variables defined for elements b sub I in omega, such that f of b1, comma dot 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 b sub n is in the script f of bn. Remember, the script f of bn is the collection of choices for white in each step, in each turn. Now, a sequence f1, f2, where f sub n is in capital F, equals to 1, 2, will be called a strategy. A strategy is called a F G S winning strategy if the following holds. Let B1, B2, W1, W2, be sets such that B1 is in omega 1 prime and Bn is in G of Wn minus 1. Your n is from 2, 3, all the way to infinity. And secondly, W sub n, which is determined by this n-step strategy, and which is in turn in script f of b sub n. Here n is from 1 to and this implies that the intersection of the alpha of bn's, which is the same as the intersection of alpha of wn's, is continuous. In this case, we will call this strategy a winning strategy. Now S is an FG winning set if and only if there is an FGS winning strategy. And under these circumstances, white will win by using this strategy.